All right, we are back. Recording is on Wednesday, October 7th, second half. So we were looking at these various assertions in this big theorem about the Fibonacci numbers. We define their generating function. There's this power series that has them as the coefficients. And the first thing we'll do is we'll show why it has this fairly simple algebraic form. From that, we're going to deduce an exact formula in terms of the golden ratio, which is phi, or powers of phi, the golden ratio. And this other thing which is related to it, phi is 1 plus square root of 5 over 2, and beta is, so to speak, its conjugate pair, 1 minus square root of 5 over 2. And then after we derive that formula, we'll deduce, okay, therefore, that the nth Fibonacci number is approximately what you get if you ignore the minus beta to the n, because beta is smaller than 1 in absolute value, and so it becomes negligible. And therefore, the limit as n goes to infinity of the next Fibonacci number over the previous one is approaching this fixed ratio, the golden ratio. And this in fact statement that I wrote that I think somebody was suspicious about, in fact, is wrong. Okay. I went to look at the Wikipedia page on Fibonacci numbers just to remind myself what was true. And this thing with the brackets on top and bottom, this may be what you were talking about, William. I mean the rounding function, the nearest integer. Not necessarily rounding up, not necessarily rounding down. But those brackets on top and bottom means that. Or there's another way you could fix the formula. If you really want to use always rounding downward, what you can do is just add a half to 1 over square root of 5 plus phi of n. If you correct it by adding it a half, you'll never be so close to that nearest integer that you have to worry about whether you're rounding down or rounding up. You'll always be rounding down. Okay, so before we derive it, I want to go back to to the golden ratio and the beta. So phi, which is this golden ratio, and its buddy, the beta, 1 minus square root of 5. What did they have to do with anything? Let me just remind you why they were called the golden ratio. So it's supposedly the most pleasing ratio for the length and width of a rectangle. In architecture, in art, and so the most pleasing ratio x here, if you want to have a rectangle and the other side, let's say, is 1, so that the ratio between the sides, if the length to the width is going to be most pleasing, people thought that should be the case in which this unit square here, so I'm making this also a 1, right, so that's a square, makes this rectangle here have the same ratio. Of the length to the width. So same ratio as the big one. In other words, x over 1 should be the same as the ratio of, now we have to figure it out, 1 to, no, not 1 minus x, but x minus 1. Okay. And Theo's saying, I think phi minus 1 is equal to 1 over 5. That might be the same thing. Let's see what happens when we try to derive it from what I'm saying here. We want x over 1 to be the same as 1 over x minus 1. Maybe that's the same as, it's close. Anyway, let's see what happens. We get x squared minus, well, sorry, I'm cross multiplying here. X times x minus 1 is equal to 1. X squared minus x equals 1. X squared minus x minus 1 equals 0. We get some kind of a quadratic equation, and that might be the same as what would come out from yours, Theo. I'd have to check. But the point is we can solve that quadratic equation, right? So x is going to be, what is it, minus that -1, so +1, plus or minus the square root of b squared minus 4ac is going to be -1 squared minus 4 times 1 times -1. Okay, so we get something under the square root sign. It's not too bad. We get a 2 down here, and the dust settles. What's under the square root sign is 5. And so this is our phi and beta. And so this is where they came up first historically. So this was just a little aside about why is it called the golden ratio. Everybody okay? All right. So I propose we just start proving the things I claimed that we would be able to prove, like about the generating function. And let's go back and steal some of the stuff. Let's start with this, part A. Try to derive that first and see if we can get to the rest of the things. Oop. Okay, so everybody good? Questions before we start this? So here's how it works. This is the general method. You start with the recurrence relation and the initial condition. I'm putting the strategy is on the side here. What did our recurrence relation say? It said fn plus 1 is equal to fn plus fn minus 1. That was valid for n at least 1. And then we had f0 is 0 and f1 is 1 as our initial conditions. So what we do is we multiply both sides by x to the n, and we're going to sum on n. And I'm being careful to only sum from n goes from 1 to infinity there, because this thing was only true for n greater than or equal to 1. Okay, everybody see what I did there? And believe me, that's the place where one most often makes a mistake, is not starting the summation at the correct place that matches where the recurrence began. That's the place where you're most prone to make an error. And I'm going to be incredibly careful now to watch where those summations are beginning. I might even change them a bit, because this thing looks really close to our original f of x. What I'm going to try to do is rewrite everybody in terms of little f of x. And this one's very, very close. It won't be hard. But I'm going to try to adjust this one and adjust this one. Since their subscripts on the f doesn't match the power of x, I'll try to fix that. So over on our strategy side, let me write down. First, you start with the recurrence relation. You multiply by x to the n, sum on n carefully. And then we're going to get what's called a functional equation for f of x. You try to rewrite everything in terms of the generating function. All right, so this one, let's let's be careful. This thing, I claim, is just f of x, but it's missing the n equals 0 term, right? It starts at n equals 1. It doesn't have the n equals 0 term. So I'm going to subtract that. I'm going to say, oh, it's f of x minus the x to the 0 term. Okay? This one doesn't look right because that power of x doesn't match the n minus 1 there. That's an x to the n, that's an n minus 1. But what's stopping me from factoring out 1 power of x? So I'm going to rewrite this as x out front. X goes from 1 to infinity, fn minus 1 x to the n minus 1. That's okay. These were all, because n went from 1 to infinity, everybody here did have at least 1 power of x that I could factor out, and I just stuck it in front. Okay. This one is not quite right. Let's see what's happening there. Yeah, actually, I think I'm going to do it in such a way, right? I'm going to divide by an x. So I'm going to write 1 over x. N goes from 1 to infinity. F of n plus 1, x to the n plus 1, right? Because what did I want to happen? I want the subscript on the f to match the power, and this guy was 1 too small, so I just adjusted this by 1 over x times that. Did everybody see why I did that? All right. Now, this is in a much better situation. This is this guy plus x times, all right. Now looking at this one's quite nice to write in terms of little f of x. It goes n from 1 to infinity, but the subscripts are fn minus 1, the power is xn minus 1. This actually starts f0 x to the 0, then f1 x to the 1. This one is just on the nose f of x. It's not missing any terms at the beginning. Okay? And this one, what do we got here? We got a 1 over x. This one starts, n goes from 1 to infinity. It starts with an f2 x squared and then f3 x cubed. So it's not quite little f of x, which would begin with the x to the 0 term. It's missing the x to the 0 term and the x to the first term. So I'm going to say it's f of x minus f0 x to the 0 and f1 x to the first. All right, so everybody see how I was trying to be really, really, really careful there? Because these are the places where one often makes a mistake in doing these manipulations. Questions? Now we're really close to getting our functional equation for little f of x. These f0 and f1s, remember, f0 is just a 0. f1 is just a 1. So I'm just going to rewrite this. 1 over x. F of x minus f0 is nothing. And then I've got a minus x to the first is f of x minus f0 is nothing, plus x f of x. And I could rewrite this as f of x minus x. Let me multiply both sides by x. So I get x f of x plus x squared f of x. And now what am I trying to do? I'm really trying to solve for f of x. So I'm going to bring all the terms that have an f of x over to one side. Which side should I bring them over to? I don't know. Minus x is, let's say, x squared plus x minus 1 times f of x. Is that right? Did I do that right? I'm worried that it looks like I did that wrong. No, it looks okay. Oh yeah, sorry. Now I see, it's because the minus in front of the x. F of x is minus x over x squared plus x minus 1 is x over 1 minus x squared. And that's what we were trying to derive, right? That was the thing that we see up at the top. Okay. So the key point is you get this functional equation here. Let me maybe make this the steps color coded. You start with the recurrence relation. The functional equation is what I would call this thing right here that we derived at this stage. And then what you try to do is solve that functional equation for f of x. And this is the place where quite often you have to use different techniques. We were just able to do it just monkey around with some algebra. Sometimes the functional equation gets phrased more in terms of a differential equation or an integral equation. And then the technique that you have to use for solving it is, might be different, might be more differential. Whoop, didn't mean to do that, sorry. Let's grab the solve, because that's what we did here, was the solving part. Ah, didn't mean to do that, that's for sure. Let me try this. Oh, what color? Pink. Got too much stuff in pink. Okay, but that's step A. Everybody good? Questions? All right, let me go back and steal B. From this, we will deduce this. All right, so let's do this deduction. And the point here is that 1 minus x squared, that denominator, I'm going to want to take this expression, which is a little bit hard to work with, right? Remember, this is a power series in which the power on, the coefficient in front of x to the n is my Fibonacci number. I want to extract the coefficient of x to the n in this expression. Looking at it in this form, I don't know how to do that exactly. I don't know how to get something simple. But if I was to write down something like a partial fractions expansion, then I could use the geometric series tricks that we already know to extract the coefficients. So that's my point, is I want to write this as a sum of geometric series. Let's rewrite f of x using, first of all, that denominator. I'm going to factor it into two factors, in fact, two familiar factors. 1 minus phi of x, 1 minus beta of x, all right? So let me check this. Check, right? This guy is 1 minus phi plus beta of x plus phi times beta of x squared, right? All I did was multiply it out. Again, I got this quadratic. And remember what phi and beta are. They are this 1 plus square root of 5 over 2, 1 minus square root of 5 over 2. and 1 plus square root of 5 over 2 times 1 minus 5 square root of 5 over 2. And so the claim is this thing in here, this square root of 5 here has a plus, here it has a minus. So I'm just getting 1/2 and 1/2, all with a minus sign in front. That's just a 1 minus x. And here, what's happening is in the denominator, I get a dividing by 4. In the numerator, I'm going to get 1 minus the square root of 5 squared. So it's 1 minus 5 is negative 4. Negative 4 over positive 4 is a minus 1. Okay, we just checked that. So that's the key point. This is why the phi and the beta show up, is because when I want to try to write this quadratic as 1 minus a real number times x and 1 minus another real number times x, this is not exactly factoring into its roots. It's factoring this quadratic into the reciprocals of its roots, but it's very, very close. It turns out, by the way, that the reciprocal of phi is negative beta, the reciprocal of beta is negative phi. Okay, so this has to do with their definitions in terms of the golden ratio. So now the point is, one can do partial fractions the same algorithm. I'm not going to do it here for you. I'm just going to give you the answer. The one that you learned in calculus to write. All right, so our f of x was equal to x over 1 minus x squared. Now we said that that denominator could be written as 1 minus golden ratio times x, 1 minus the other thing, the not golden ratio, but it's buddy. And you can write this as a constant over 1 minus phi of x plus a constant over 1 minus beta of x. And I'm just going to tell you the answer. Those constants are 1 over square root of 5 and negative 1 over square root of 5. So right here, this equality is the partial fraction algorithm that you do just like in calculus. To do that rewriting. Where do we get the idea about how you could try to do this? There's some unknown coefficients. You call this like an A and this one a B. You rewrite it and you solve for the A and the B. Everybody believe you could probably do that? Okay. That's good, because this thing now looks exactly like one of my geometric series. This thing looks exactly like a geometric series. I know how to extract the coefficient of x to the n. So I'm just going to rewrite them like geometric series. I get a 1 over square root of 5 times just the sum. N goes from 0 to infinity of phi to the n. That's what this guy gives me, is this. Oh, sorry, I'm missing an x to the n, excuse me. And the other guy gives me a minus 1 over square root of 5, and then a geometric series of beta to the n, x to the n. So both of those were just using geometric series. One over 1 minus r is 1 plus r squared plus dot, 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 dot. Everybody okay? And so now the point is f of x, right? This was supposed to be the sum of the Fibonacci's times x to the n. Just putting this all together is sum n goes from 0 to infinity of 1 over square root of 5 phi to the n minus beta to the n, x to the n. Right, all I did was just combine these two summations and look what the coefficient on x to the n was. And that's what we wanted. Beta doesn't look very good. Everybody see how that went? Okay, so going back to our plan. Whoops, lost the plan. Solve the functional equation. The next stage where sometimes it's hard and sometimes it's not so hard. Here we were able to do it is extract the coefficient of x to the n in the generating function. And that extraction procedure, there's a lot of techniques that have been built up over the years to try and help people to do this. No, let's do blue. There's sometimes where instead of extracting it exactly, like we just got an exact formula, people have techniques. For example, they use complex analysis to estimate it. Rather than getting an exact formula, they at least can get the asymptotics for it. All right, so that works more often than the exact formulas, but sometimes you can get it exact. Whoops. And I think there was a part C was the only other bit, but there's not too much to say about part C. Let's just copy it again. What was part C saying? Yeah. So I don't know if I'm going to say much about part C. I'm having a little trouble grabbing it though. Actually, what I want to do is grab it together with the exact formula. Oh, I missed part of the exact formula. That's okay. We'll fix it. Oh, I totally missed the exact formula. The phi is and the point here is simply to say that the limit as n goes to infinity of this guy is 0 because it's smaller in absolute value than 1. And in fact, the point is once you get to like beta squared or beta cubed, it's actually smaller in absolute value than a half, which means this formula is going to be correct and this formula is going to be correct. You know that the Fn is this thing minus this thing times divided by square root of 5. And because that thing divided by the square root of 5 is so small, all you have to do is do the rounding and you see that it's going to be correct. And Jack's asking, do people have some hint that Fn would use phi and beta? Yeah, so that's the thing is that they very quickly from doing those, just the experiments of the ratios, people saw, where is this? Where did we talk? Yeah, they did this experiment, Jack, of looking at the ratios and noticing that like it starts out 2, 1.5, 5 thirds, 8 fifths, 13 eighths. They looked at the decimal expansions. They saw that it was approaching something like 1.618, and they could do many, many, many terms. So they had some idea that it was approaching something that they also knew about from architecture and art was the golden ratio. So then they kind of thought about it the way the book presents it. The book says, well, it looks like it's kind of a geometric series. It seems to be growing close to a geometric series with phi, the golden ratio. So maybe we should just assume it had the form of being a geometric series and figure out what the ratio could be. You realize the only two possible ratios are by solving a quadratic, it would have to be the two roots of 1 minus x squared, and only one of them was a ratio which is bigger than 1. So yeah, Theo asks, what does f of x represent? That's a great question, Theo. So this whole technique where you talk about generating functions, right, is crossing your fingers that the sequence, right, trying to write down the 0, 1, 1, 2, 3, 5, and 8, which is an infinite set of data, you hope that somehow, even though it's infinitely many numbers, there's really something finite about it. You know, because of the recurrence, somehow, even though there's infinitely many numbers, there should be some more compact, finite way of representing it. And this f of x, this generating function, it is one compact form of doing it. There's kind of a similar idea, actually it's the same idea, gets used in signal processing. People talk about a sequence of numbers as being like a signal. And there's something called the Z transform, which says, oh, instead of thinking about them as a bunch of numbers, stick them in front of powers of Z, you know, like the nth thing in the signal is you put that in front of Z to the n, sum them up. And they call that the Z transform. It's like this finite way of presenting this infinite set of data that's more compact and then lets you manipulate it. But I can't say that it has any meaning. It's just what's called the generating function. It's an extremely useful tool once you get used to using them. But it's a really good question. Okay, so we have hit the end of our proof of the, yeah, so I'm just saying not much to say, right? The point is the end of this proof is not much to say in proving this, except that proving this, except, right, Fn is equal to this guy, you know, plus error term, which is exactly, you know, minus 1 over square root of 5 beta to the n. And this approaches 0 as n goes to infinity. And you just, you know, check how quickly is it going to 0, and therefore are these two formulas correct? Okay, so what I'm going to have to figure out is for next time, we might actually do another counting problem, the Stirling numbers of the second kind. You know, it has an answer, and it's an interesting situation because Stirling numbers of the second kind, even though they come up for many counting problems, they answer sort of an obvious counting question, they don't have an exact formula. They only have a decent generating function and a decent recurrence. So you can tabulate them by recurrences, you can write down a generating function, but there's really no simple closed formula for them. And so it's one of these situations where you have to just deal with it and say, maybe a generating function is not so bad. You can still deduce things about them. I have to decide whether we're going to do that by doing some group work, or we may just start moving on to chapter 7, which is about graph theory. So we'll think about what we want to do for next time. Yeah, so any questions? I guess we're, in some sense, we're ending, no, we're not ending early. We went over in the first half, but now the second half is accordingly shorter. Any questions before we turn off the recording?